What is going on, everyone, and welcome to another machine learning tutorial. In this tutorial, what we're going to be doing is continuing along with classification, and specifically right now we're talking about k-nearest neighbors, which takes any new data point and just compares the quite literally Euclidean distance between that point and the other data points to determine which class it happens to belong to by comparing its kind of distance from one class to another class, basically. So we're going to be using Scikit-Learn to do this, and then we're going to use a data set from the uci.edu data set. So here we go. So this is for University of California at Irvine, I believe, is UCI. Okay, so this is the website. If I happen to forget, it's relatively simple: archive.ics.uci.edu/ml/datasets.html. They have a ton of datasets here. They've got them, I'll even scroll up here. They've got them separated by tasks that you would perform with this dataset, like classification, regression, clustering, they've got attribute types, data types, the area, or like kind of environment, right? Like sciences, engineering, social sciences, and so on. How many attributes, and then how many instances, so probably samples here. Anyway, there you have that. It's a great site for practicing machine learning. And the data set that we're going to use is the breast cancer data set. We're going to go with the original one. I've already got that up, though. So that would bring you to a page like this, and then you'd be interested in the data folder, which would open up this page. And then if you click both of these, you'll get this and this. So the first one is the actual data that corresponds to the breast cancer set. So we'll right click and save that. And I'm going to save it in the folder, or the thing that we're working in, which is this right here. And then the second one, actually, yeah, I'll just save it there. The second one is, we don't really need to save it, but you want to read these because this gives you a little bit more information on the data set itself. Primarily, first of all, you got the citation request. Also, you have coming, let's see, past usage. You can learn about like who's used it and stuff like that. And then basically we're looking for, yeah, right here. So the dot names, right? We didn't know which one of these, like what anything was. But if you come down here, you can see, so the first column is just sample code number, basically an ID. The second column is clump thickness, and then uniformity of cell size, shape, and so on. You keep going down the list. And then finally, the 11th attribute is actually the class, which is either benign or malignant for the tumor. So benign or malignant is an attribute, but that's also what we're actually trying to predict for. So we're going to actually make that the class, or the label, so to speak. So anyways, that's our data. We've downloaded the data. I have it now. Let's see if it's, yeah, down here. So I'll open that up. And so here's the data. And what I'm going to go ahead and do is add a header row here. We could do this in pandas, but it's probably easier just to type it in really quick here. So we know the first thing is ID, clump underscore thickness. And you'll definitely want to be doing this along with me. And then I'm going to say unif cell size, unif cell shape, and I'm going to scroll like this here or something. Let's do that. And then this. Okay, unif cell shape, and then what do we have next? We have marge adhesion, single epith cell. I think that's saying size, I'll guess. Bare nuclei, bland crom, we'll just stick with that. Norm nucleoli, mitoses, and then finally class. And so hopefully we have the right number here. So ID 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, cool. So the thing that to pay a little bit of attention to, we'll save this, is that 11 is a class, 2 means the tumor's benign, 4 means it's malignant. So you'll actually see later when we go to code this ourselves, most machine learning algorithms don't want the class to be a string, right? It's supposed to be a number. So this is how you can convert it. But later on, I'll show you, you can kind of get away with using a string. But anyway, for the most part, you're going to be using like NumPy or some other really optimized library that does number crunching, and that's going to want numbers, not a string. So the other thing to pay attention to is this says it does indeed have missing attributes. There's 16 missing, and if they are missing, it's denoted by a simple question mark. Also, you get the class distribution here, which just says basically we've got 458 benign tumors, and 241 of them are malignant. So it's not totally a balanced data set, but it might actually be more realistic in terms of how many are benign or malignant. I'm not really sure, but hopefully more people have benign tumors than malignant. So anyways, that's the data set. We can rename it, and now let's go ahead and load it in to what we're working in. So just remember that name, and hopefully it's saved in the local directory. So let me move all this stuff over. I'll put this down here. And so the first thing we need to do is handle for the missing and bad data. But first, let's go ahead and make some required imports. So import numpy as np. From Scikit-Learn, we're going to import pre-processing, cross-validation, and neighbors. So you should recognize pre-processing already. We've already covered that. Cross-validation, already covered that. Neighbors is new, but you can probably guess what that's going to be used for. And then we're going to finally import pandas as PD. Again, we've already kind of been using that. So first of all, we're going to load in that that CSV, or actually it's just a text file, but we'll treat it like a CSV because that's basically what it is. We're going to load that into a data frame. So pd.read_CSV, and the name is breastcancerwisconsin.data. So I'm just going to copy and paste that. That's the name. We'll read that in. And we already know out of the gate we have some missing data that is denoted by a question mark. So let's go ahead and replace that information. So we're going to say df.replace, and we're going to replace all question marks with a negative 99,999. And then we're going to say, whoops, comma, in place equals true. So that just modifies the data set or the data frame right away. And then, remember before I was asking, is there any, you want to watch out for useless data. And in this case, what might be useless data? Well, when looking at the data set here, the first column is ID. Does ID have any implication as to whether or not a tumor is benign or malignant? The answer, of course, is no. So we don't want the ID column. That's a completely useless column, and it's going to lead our algorithm astray. Unless I happen to forget, we're going to get rid of it for now, but later we'll bring it back just so you can see how much havoc that might wreak on our algorithm here, especially k-nearest neighbors. Other algorithms might handle for outliers better, but you'll see how bad k-nearest neighbors handles for outliers. So anyway, df.drop, and we're going to drop what? We're going to drop, put that in brackets, the ID column. Pretty sure you can get away with just string, but I know brackets will work. Anyway, 1 there, and then in place equals true. So we're dropping the ID column. Now, as you can remember before, we're going to define our X's and Y's. Also, I believe I've already explained the negative 99,999. The whole point of that is just so most algorithms will recognize that's an outlier and will treat it like an outlier as opposed to dumping the data. Again, a lot of real-world data sets have a lot of missing data, just a ton of holes, to the point where if you were to drop everything with missing data, you would maybe sacrifice 50% of your data set or something like that. You don't want to do that, and you don't have to do that. So anyway, we do this to make it just a huge outlier, basically, at least for that specific point. Now with k-nearest neighbors, this really doesn't do too much. Try to envision, like if you just had two-dimensional data plus the class, try to envision what negative 99,999 would do. That's really significant. So the only time you would ever identify probably with a class that had if your current one or your current feature set has this, would be comparing it to another feature set that also almost certainly has one of those. But anyway, we're going to have that there. So maybe in this case, you might want to actually say 0 or something like that. You just kind of keep that in mind, depending on how you want to do it. We'll see that this probably won't have a huge effect anyway. Also, we only had 16, so you could, in theory, rather than replacing the question mark, you could do df.drop NA in place equals true, and just get rid of those. So anyway, that's really, it comes down to opinion and also your specific data set and the algorithm that you're going to use. But anyway, we're going to do it this way. So now we're going to define x and y. So we've got x and y. Again, capital X is for your features. Y is for your labels or your class or whatever. So x is going to be np.array. And we're going to do basically the exact same thing that we did before when we were using linear regression. So the features are basically everything except for the class column. Class. df.drop class, comma 1. And then the label is basically just the class, right? So np array df class. So now we have our features and our labels. Now we're going to do the cross-validation. So again, x train, x test, y train, y test equals cross validation dot train test, dot train test split, and we're going to split what? X and y, and the test size will be 0.2, so 20%. Feel free to change that if you want, but this line, again, we've already covered it. That's just how we can quickly shuffle the data and separate it into training and testing chunks that meet our hopes. So now we're going to define the classifier. So you've already seen this before, so or not fit yet. Classifier equals neighbors.k neighbors classifier. K neighbors classifier. Okay, I think I spelled that right. So we've defined the classifier. Now we can fit. So clf.fit, and then we fit what? Well, we fit the x train and y train. Again, all this code is almost identical to when we did the linear regression code. That's what's really just so nice about Scikit-Learn, is even with different machine learning algorithm, I hate to say classes, but really they are classes, right? Before it was regression, and regression is totally different from classification. But as far as Scikit-Learn is concerned, it's basically the same thing. So we fit the data, and then of course we can immediately test it with, we'll call this accuracy, equals clf.score x test y test. And again, we're calling this accuracy. I may forget to change it in the written version, but we want to call it accuracy and not confidence. Like a lot of times I want to call it confidence, but really it's the accuracy, because we can also measure confidence, as I already kind of explained in the theory part with k nearest neighbors, when it comes down to the vote, basically. So there's our accuracy, and then we'll print accuracy. And let's go ahead and save and run that. It's taking a while to pop up, but there it is. Let's pull it down here. Oh, it's telling me the file does not exist. Sure it does. Liar. Maybe it's oh, I know what it is. So I downloaded .data, but it's actually, I bet it's .data.text. Let's try that. Yeah, interesting. Okay, so with just with the defaults and all of that, our accuracy is 0.964, which is 96.4%. That's huge accuracy. Now, of course, like I said before, with the self-driving car and all that, differentiating between a baby and a blanket and a blob of tar on the road. I don't know about you, but I don't want to be told that I do or don't have cancer even with a 4% inaccuracy, right? I want like 99+%. But probably, you know, I would go off a test that was 96.4% accurate. Now I'm thinking about it, let me comment out the dropping of the ID column, and let's just see what this does. Bam. Massive. Like, we're almost to flipping coin status just by including the ID column. That's huge. Okay, so finally, the next thing that we're going to go ahead and do is we're going to make a prediction. So let's say you've trained this classifier, in most cases, especially if you trained on a huge amount of data, we would pickle the classifier immediately. We just save it to a pickle. But I'm not going to do that every single time. So if you want to know how to save classifiers, go back to that one. This just trains and tests so fast, it's not really that necessary. So anyways, now let's make an example to predict. So let's say example underscore measures equals, and this is going to be a numpy.array. And let's just make some up. So let's say 4, 2, 1, 1, 1, 2, 3, 2, 1. So first thing we're going to do is, let me pull this over. So what ought that predict? So keep in mind, this is the first few minus the ID and also minus the class. So it would be like these numbers here. So a 4. So automatically, like looking at this, it looks like this first column is kind of higher for what I believe to be malignant. I think 4 was malignant, if I recall right. Anyway, it's a 4 class. Every time that's pretty high, that's a 4. So you can look at that, but also the other numbers seem to be in line with the 2 class. Also, I mean, you can make up your own if you want. Just go ahead and search the document and make sure that does not exist. 4, 2, 1, 1, 1, 2, 3, 2, 1, right? That set of attributes does not occur anywhere in this document. Therefore, it's unique. It's never been seen before. So we're going to test on that. So there you have that. And now to do a prediction equals clf.predict. You've also seen this already with linear regression. So again, it's just the same no matter what type of algorithm you're doing, it's just nice. And then print, we're going to print the prediction. And we're probably going to get either a warning or an error here, but I'll explain that next. I didn't want to add that to the list. Oh. Let's see, example measure. Okay, so example measures. I got an error because of that. Bummer. Okay, so we're actually getting an error that I didn't expect to get. Oh! Oh, let's see. What we're doing, I forgot to uncomment out the ID column. So let me go back because I am confident now that we'll get our prediction. Sure enough, there we go. Okay. Haha. So what tipped me off was that our accuracy was still 56%. Okay, so now our accuracy is 98.5%, and we did get our prediction. But you'll see we got this deprecation warning that it wants us to reshape our data. Before, the problem was we were passing an incorrect number of attributes because we had one more because of the ID column. Okay, anyway, fixed. But now to get rid of that value error, we would do this, and then run it. And then now you don't have this stupid deprecation warning. So that makes things maybe a little more complex. So I just want to, before we zip away, we're done with k-nearest neighbors, but now we're talking about working with Scikit-Learn and also NumPy as far as reshaping and shapes are concerned. And I think it's important to understand how this works because it's going to come up. So, so in this case, we had one sample. So we had one -1. So what if we had two samples? Like what if it was like this? Like copy this. Let me think here. I think we can get away with, it's got to be a list of lists. So it would be a list of lists. We'll do comma, paste. And now I've got 2. And let's change this to like 2 and then this to 2. And so we've got, basically we've got 2 samples. So noting the directions we had before, this was for 1 sample. So we're going to change that to 2. Right, so let's go ahead and save and run that. And you'll see we got our 2 predictions, 2 and a 2. So it was able to do that. But then what happens when you have an unknown number? Like you might have an unknown number of predictions. Maybe this week you've got 15 patients. Maybe next week you've got 45 patients, right? That's going to be very common, and you don't want to have to hard code the shape every single time. So what you're going to need to do is rather than when you go to reshape, at least program wise, I don't know any better way. Like converting like a list of lists or making a list of lists based on a data set, super easy. Converting to a NumPy array, super easy. I'm not sure how to properly shape it automatically to the shape that Scikit-Learn wants. But what you can do is once you've made this list of lists, once you're ready to convert, you've converted it already to a NumPy array. Once you're ready to reshape, all you have to do is you've got measures.reshape here. We're going to say rather than reshaping to 2, -1, you just replace 2 with the len of example measures, right? And now example measures can be any length, right? We'll still run it and we'll still get a report back that is 2, and that is how you can program it in to just automatically predict on any number of predictions. And again, this is not k-nearest neighbors specific. This is any of the Scikit-Learn classifiers, and then in general, just how to properly reshape your NumPy array for a variety of reasons, but that's just one of the reasons why you would, is so you can feed it through Scikit-Learn. Okay, so there's your real-world example. We found that we can predict based on, somewhere between 94 and 98% accuracy, which is pretty impressive, especially now that you know the intuition of how simple k-nearest neighbors is. And now what we're going to do is actually write our very own k-nearest neighbors algorithm. And then what we can do is we'll run it on these exact same data, and then we'll see how we compare to Scikit-Learn. Now, just thinking logically here, knowing how simple k-nearest neighbors is and exactly how it works already, should we perform accuracy-wise similarly or exact or what compared to Scikit-Learn? So think about that, and in the next video we'll actually start writing our own k-nearest neighbors algorithm from scratch. So if you have any questions or comments, leave them below. Otherwise, as always, thanks for watching, thanks for all the support and subscriptions, and until next time.